Lost boy I never met, usually hanging out with Peter Pan. And when we're bored, we play in the woods, always on the run from Captain Hook. Run, run, lost boy, they say to me, away from home.
Hi, good morning. So, a sec. Hi, Anchen. Thank you for coming. And now you are the co-host. Can you hear me? Okay, thank you. Welcome. I cannot stop thanking you for coming this early. As usual, we still have a large number of people joining our session. So please take this time to ask me questions if you have any. Maybe some small matters. Recently, I got large number of inquiries, especially about assignment 2. So for whatever question, if you need to contact me in any way, please try to follow the communication protocol that we have listed in the FAQ in the Get Started module. So your inquiry will be addressed in time. I got several questions in the chat. One, I got a question that like in the assignment 2, I'm not very sure what do you mean by the code section. If you want to mean the section that you discuss your implementation of the algorithm, yes, the answer is yes. You can copy and paste code from what we have learned, both from weekly exercises and also from the tutorials that I have left online for you to follow. And also you can follow my in-class examples. We do not check duplications in code. However, we do not do marking solely based on code either. We mark according to how you have demonstrated your understanding of the algorithm. So you need to write something from your own understanding anyway. Another question is how about to develop multi-layers of perception? That is a great idea. But I'm not sure if you have already done some work on that, it's fine. But if you want to take some time to develop that maybe I'm not sure if the time is enough for you to finish that. Yeah, multi-layers perception is good. And also if you, I have already published the neural network modules, so you can take some reference from there. I got another one. Yeah, I apologize so much for the one-to-one consultation yesterday. I missed that because I checked the timetable and I checked the wrong week. So please stay with us for a little longer after this session. I will be answering questions then. And if you want some one-to-one conversation, yes, you can also email me and book a time. I think as early as possible. Sorry for that. Another question is about how to run our code. We addressed that in the okay. I do not, because I do not remember which session. I cannot refer you to that one, but I definitely have mentioned that. So for okay, so let me share my screen first. So okay, here is a screen, and the example, let me find the example. So when we are marking, we will not try to prepare the data for your experiment. We will just hit the run all function. So your code should work in that way. Where is that? A2 examples. Hide. Okay, here is an example. Look, when I'm accessing the as a marker, when I'm accessing this one as your submission, I will just do run all. So it is your responsibility to make sure this will work. If, for example, you want to work on some data set that is outside machine learning foundation, sorry, that's also outside the Colab or the machine learning libraries, we have shown an example. You need to check previous sessions. In one session, I demonstrate that you can insert, not this here, code snippet. You can insert some code that allows any user who uses this notebook from downloading file, no, not to your local, but where is that? Maybe open, because I need to demonstrate that the font size is a little bit large. Okay. Oh, because it is running, so it takes a while. After it stops running, you can anyway, you can find that in the code snippet tab here. It gives you some suggestions on how to download. By download, what I mean is not to download to your local computer. Please be aware of that. Your local computer is here, and you are operating virtual machine on Colab here, okay? And by download, what means is this virtual machine, your Python code can download file to the virtual machine, and this download could be from your own Google Cloud storage. Okay, it allows you to download file from your Google Cloud storage. Please make sure you have set up the permissions correctly so that we can run that. You can ensure that by ask one of your classmates or friend to run your code from their account login. So how many questions do I have? I maybe last 3. Yeah, we will wait for training to run. But if you are going to work on an industry level large data set, please let us know. Otherwise, for a data set such as Iris or anything that you can directly use from scikit-learn, the training would not take too much, like 1 or 2 minutes. Well, you can create the data set, you can create your own data set, but just to make sure that we can access data set. You do not like something, well, every time I run my code, I need to drag a local file from my computer into the upload session, because we do not have that local file. If I build a perception, does it have to be multi-layered? No. You can implement the native perception, the vanilla perception algorithm we introduced in session 3 and session 4. A certain amount of accuracy, your accuracy won't be taken as a criteria. However, if your accuracy is unreasonably low, such as in the ARIS, usually people get 97, 96, but your algorithm get 60, then probably this will be thought as not correctly implementing an algorithm, unless you have adjusted something that caused this inaccuracy and you have discussed that. And can I share Google Drive? Yes, you can. Maybe not a folder, perhaps a zip file should definitely be okay. And you can unzip zip file easily in the Colab. And you can share that with other people. Please refer to for the data part. First, the easiest solution is use the data that comes with scikit-learn. Then you do not have this trouble at all. Or alternatively, if you really want to use your own data, please refer to, I think, a discussion somewhere in week 5, week 6, week 7, these 3 weeks. I have demonstrated how to download data from Google Drive. There are 2 authentication. The key points are 2 authentication. One is the owner of the data need to allow everybody to use the data. The other is the user of the notebook needs to allow the notebook to download the data. For the second part, don't worry about that, because every time we will allow that. But for the first one, you as the owner of the data need to give access to everybody. Okay, there are so many questions. Let's try to address more. Real world data is more preferable, but toy data is definitely okay. The focus is on your understanding of the algorithm. I got a question, 99 on Iris, but 85 on digits. Okay, that's fine, especially if you think the digits part, the digits data has 10 class classification. What does that mean is in Iris, you consider a 3 class classification problem, and if I'm doing nothing, I just randomly guess. So for example, if you give me a class, give me a sample, I do not even look at the sample. I just see, okay, class 1, and then, okay, class 2. Then in this random guess, I will have 33% of accuracy. However, in the digits case, it is a 10 class classification problem. If I do the same, like I just see digit 1, digit 0, digit 6, I will have only 10% of accuracy. So considering the improvement from the random guess, you did not do too much worse. Okay, I address that. We do not mark you mainly on the accuracy. As long as it's past something, then it is irrelevant. Do you want, I do not understand that. I'm not sure if I understand that correctly. So you said if you use the pre-built classifier as a comparison, yes, as a comparison, yes. Yeah, as long as, see, you can argue that your accuracy is much higher than random guess, then don't worry about accuracy. You can simplify the next question is, can we simplify the data set from 2 attributes into 2? You can do that. However, that will make your life harder, more difficult than easier, because think about that. Previously, you have 4 attributes, and then you have richer information to do the classification. And if you simplify that, that will make things more difficult. What I'm doing in class, why? Because that makes my life easier, because I need to draw them to show to you. However, you do not need to draw the data set, so for attributes is easier. Next one, yes, you can use the spot data. I have another one is also about accuracy. Try to do not to worry too much about accuracy. You think about the random guess on the data set. As long as you are significantly better than the random one, you have some point to argue. Well, the focus of the assignment is about your understanding of the algorithm. Yeah, do not put too much effort on improving accuracy, unless you can put your effort in your report. Okay, sorry guys, I think I have to stop here. We have been 15 minutes in the session. We need to start our today's schedule. So if you still have more questions, I'm still here after the session for half an hour, maybe a slightly longer, to compensate the missed one-to-one session yesterday. So anyway, we start today's study. Allow me to reorganize my screen. It's a little bit messy here. Open. No, this is the next one. This one. Sure. Filters for me. Okay. Well, as usual, let's welcome back from the Stilweg. Let's review a little bit about the big picture. Where are we? We start from learning machine learning as software 2.0. So okay, my pencil needs some recharge. I'm joining here. So from the software 2.0, we understand we want the machine to program itself. We need data from which it will learn. We need to believe there are trains or some extensible laws or rules that is waiting for being discovered. And we do not have those trends, the trend explicitly given. Otherwise, we do software 1.0 and program machine myself. And in the second session, we consider the discovery of the trend procedure. We have data. We have a hypothesis set. Hypothesis set consists of all different kinds of possible trends that we would like to consider. It is a limiting factor because it forces us to explicitly saying, okay, this is all the possibilities I'm going to consider. I will not consider anything else. And we have a selector. So this is an algorithm that helps us to select one candidate from the hypothesis set, and that is according to some laws. And in session 3 and session 4, we have studied our first our first model family, which is a perception model, and it is just to cut the data space in two parts using a flat thing, a line, a straight line, or a hyperplane, anything. It's an easy cut. It is implemented by giving each data attribute a weight. Consider that is your data table, okay, and we give each column to, we represent the model in such a chart, and we take the sum of each attribute, and this will make a number. And the assumption here is anything that could be determined from a sample is determined from this one number. Well, we then develop a geometric view of this calculation. We think of W as some direction or vector, and the particular value of X as another vector. So this will make the picture like you project the data onto a direction, and the learning would be a direction discovery business. And we have established that the geometric view of machine learning is extremely useful. In week 5 and week 6, hopefully my pencil starts working. Yeah, good. We considered another way of formulating the hypothesis, that is using if and else judgments on those individual data attributes. So, and we have developed a way of formulating those if and else statements into a data structure. So previously we are considering different possibilities of writing programs. That is software 1.0. And now we think some composable data structure that represents the same logic flow of the if and else branches that make the basis from which we can build software 2.0. And we consider how to build the tree structure automatically using some principles. Well, we find that the core technique here is when we at some point, such as at this point, we need to make sense of this subpopulation of the data. Where are the positive ones? Where are the negative ones? We need to measure how pure the target value is in this subpopulation. If it is pure enough, or if it is not pure enough, and I will try to split the subpopulation further using different data attributes, and how much I will gain in terms of the purity of the target value. So the focus has now been concentrated on the measurement of how mixed up a target quantity in a population. So we introduced the concept of entropy in information theory. So basically, excuse me, that is what we have learned in the first 6 weeks. And in week 7, we take a review of the previous study, and we have started our fundamental question. Look, in all these practice, what we do is that from a black box we get some samples. Okay, and our procedure will be anything we call that learning procedure. Okay, would be take this sample and try to make sense, make a trend that looks to be fitting according to the observed samples, and output this particular candidate. Well, but our hope is that this, when applied to the black box data population, that is really mattering, because that is what we will encounter in future in the production environment. Well, how can we be confident that will work? Okay, so with some hairy math, we've established one thing that, okay, the fundamental stochasticity, the randomness of learning is not from the entire process at all. It is from the fact that we do not control, and we only get random samples from the black box. So this black box to data samples is the source of randomness in the learning. Okay, so then with this fundamental randomness, everything we learned is random. So we want to build some confidence on the random. We start from, we look at the essential question that, okay, I can learn this, I can learn that, my learned model can produce this or that. However, at the end of the day, I want to be sure that my learned model is correct or incorrect, or within tolerance, or without out of my tolerance at each data point. So then apply this to the entire, well, so maybe this, apply this to the entire data population, we will get another black box, and this black box is the maybe let's call that correctness or error, doesn't matter, of some h. Okay, well, then the random samples in this case would be right or wrong evaluation. Unfortunately, we have established that the error evaluated in such a way using examples in training data of H. And if we consider the unfortunate fact that this is different from outside H, of course, this will have input argument of the data set. The data set is just the samples. This is greater than some tolerance. This will be a bad thing. We don't like, we want them to be close to each other. And this bad thing happens with some probability. Why it is with some probability? Because this guy is a random thing. This guy. This is the fundamental randomness of learning. And this happens with a probability that is happily bounded with respect to the, well, bounded with some quantity that decreases exponentially with n, with the size of the random sample. So if you have more samples and you have get some evaluation on the samples, it is less and less likely that in practice you will have a surprise. So that is what we have established from the beginning to the last week. Okay. Let me see if we are good to go. Fine, I'm happy. And okay, I have left one small part in week 7, which is that this guarantee is for a particular fixed arch. Wow. But what you really want to guarantee is that right? We want to guarantee some selected good candidate. By good or bad, that is according not to the it's only according to the in and it's selected by algorithm. We do not have direct control on that. So the larger H, when you have more hypotheses to consider, you risk more. So in previous lectures, we have studied two really small. One is a linear and the other is a decision tree, or well, in some case, small or easy model families. So if we can limit the how rich the candidates in the capital H is, we then have a good guarantee that whatever has been achieved during learning is likely to extend in the test stage. This is not very easy. Okay, it's a hard balance to strike. If you want the model family is strong enough, then probably you will encounter some hard time to estimate how rich it is, and then you quickly find maybe that is infinitely rich, so much so that we have lost every guarantee that we can, sorry about that, we can be sure that what is learned is useful. So there is a following this way, I mean historically in machine learning, following this way, and practically, and it's very natural to think that, okay, we have perceptions, we have decision trees. Is there any way to build more sophisticated, more complex model based on those simple, easy model families? And the answer is yes. And the answer is not only yes, but very widely applied in machine learning. So in the rest of the subject, we will try our best to cover as much as possible topics in advanced models. In this week, we will discuss something about ensemble models, which comes from a very intuitive idea that you have some hypothesis here. Do not be confused with this doodling and this one. They refer to different species. This refers to a large number of candidates H, and this, on the other hand, usually consists of only small number of H that has already been selected from some small hypothesis family, okay? Or maybe from the same one, it's also is more often. You have a small hypothesis family, you use some criteria to select one, you select another one, you select another one, and then you make a committee of them. And this committee, assumably, is more powerful than any one of it from the small hypothesis family. Okay, so that is what okay, that is what we are going to start. That is what has motivated ensemble models, which we will study this week. And in the next week, we will consider another idea of composing neural networks. Composing perceptions to make neural networks, which also forms a similar thought that I can compose simple machine learning models into more complex ones. Okay, let's consider ensemble. Well, I think we have spent some time to in this lecture. So I probably, let me think about that. I'll probably select some most important points to discuss in today's example. So here are our today's take-home points. Ensembles, that's okay. The core take-home points is extremely easy. We want several weak classifiers or predictors, and we let them to make a committee and let them to vote, and that is ensemble. Okay, and I hope that will attract you into some slightly longer story of that. Okay. And the second very important part today, we will touch is assignment 3. I will discuss a little bit of assignment 3 later in this lecture. Okay. Okay, I take a glance of the chat. Now we have some technical discussion about. Okay. The entropy. Oh, I didn't. Okay, anyway, I let you to follow your discussion. I think your discussion is reasonable about the value range of entropies. Sure. Good. Let's start our discussion about the ensemble. Of course, the principle of ensemble is pretty easy, and the details is what really matter. So let's consider a very, very straightforward method. See, if those weak classifiers has already been given to us, and first let us try to verify the idea is valid, is a useful one. See, if we have 3 members in a committee, Alice, Bob, Charlie, maybe. So let's call them A, B, C. Well, if both A and B and C, they have the chance of make good decisions at 80% and bad decisions of 20%. Like in the classifications, it could be correct in 80% and bad at in 20%. The final decision would be a majority vote of A, B, and C. So in this case, let's consider how the committee as a whole works. In a situation when A is correct, B is correct, C is also correct. This situation happens with 0.8 times 0.8 times 0.8. Okay, so that is 0.512, right? Hopefully, don't want to embarrass myself. Okay. Well, maybe let's consider a slightly more unfortunate situation. See, one of them have made a wrong decision. See if Alice is wrong this time, and the other two is also remains correct. Then this situation happens with 0.2 times 0.8 times 0.8, which is 0.128. Okay. So the committee's decision in the first case, of course, is correct. We do not worry. And in the second case, because it takes a majority vote, so it is also correct. Okay. And you can follow this line, and maybe in the second time, maybe boom, the B is wrong and the other two is correct. So in this case, that will be 0.8, 2 times 0.8. And the committee decision is also correct. So, well, we can list all the possibilities of the different decisions and the corresponding possibilities. At the end of the day, let me take a counterexample. See, if for some situation, maybe A, B are wrong and C is correct. In this case, we will have and in this case, because the majority of the committee is wrong and the entire committee, the ensemble of those predictors, they make a wrong decision. So at the end of the day, we want to summarize all the different situations. Okay, and then we get the correct and incorrect, the ratio between correct and incorrect of this ensemble. And in this case, it's not difficult to imagine that we have 3 situations like this to make wrong decisions, that is 0.096. And we still have another possibility in which all 3 have made wrong decisions, and this would be, sorry. So altogether, we have this much chance to make wrong decisions in this ensemble. Okay. However, you will find that is quite promising, and especially if you extend that to like take 5 people, 7 people, 9 people. With the number of the committee, with the size of the committee grows, the chance it will make any mistake will drop significantly. However, there is one challenge that is in front of us. The only thing in the way is where can we get those A, B, and C? Okay, to be more specific, of course you can argue, how about if we train A and then train B and then train C? Let's consider this strategy a little bit closer. One situation we want to avoid is that the committee members talk to each other and try to make a consensus before they submit their judgment in front of us and follow the rule of majority vote. See, if now we have a situation where Bob follows Alice every single time, that means when Alice vote green, such as vote maybe versicolor, Bob says versicolor. Alice say another species Iris, Bob says another species Iris. So in this case, when Alice is correct, Bob is correct. When Alice is wrong, Bob is wrong as well. Okay. This will create a situation that Alice will dominate the committee. Everything Charlie does not matter at all. When Alice is correct, everything is correct. When Alice is wrong, everything is wrong. And Bob does not do anything either. Anyway, so it is very easy to imagine that in this case, the performance of the current committee drops to the performance, to Alice's performance, because Alice determines whatever the committee does anyway. Okay, why we are considering this situation that we want to avoid? Okay, that situation points to a more general case where the decisions between the committee members are dependent. They depend on each other. If those members, they happen to work in a way that agrees each other too much, well, the advantage of letting work independently and view the data points in different ways and make them to make decisions together will disappear. Okay. So that is the big challenge in making ensemble methods. I think the system of voting, the strategy of if we happen to have even number of committee members, stuff like that, they come second. The most important thing is we want to somehow have a number of committee members that they can act independently. So why this is very difficult? How about look, if we have a hypothesis set, okay, and we let it learn from data sample, we get A, and then we get another data sample to learn, and we get B, and then we get another data sample to learn, we get C. Then A, B, and C, they do not need necessarily to agree with each other. Anyone who is imagining or somehow in your mind do not agree with me about this strategy, you can chat in the chat box anyway, and we can see if everybody are on the same page, is on the same page. Well, at least if you can appreciate that we have something to overcome here, then that's okay. For the rest part, it's easier to learn from the example of making it a burst. Okay. Anyway, I continue my discussion. The story here is the difficult part of the story here is that we do not have the luxury. We do not have the 3 sets of data. In practice, is that if we do have this luxury, we do have a very large or unlimited resources of collecting the random samples from D, we could somehow back to this strategy, like here, we can enlarge the N so much so that we have a huge N that guarantees even we have a huge hypothesis set, eventually our learning works. The reality is maybe our data size, or compared to the, and not mean the absolute size of the data, maybe you have a very huge data, but comparing to the complexity of the question, the size of the data might not be insufficient. It might be insufficient. In this case, how can we how can we form the committee from the same data sample? And that is a challenge. Okay. So with this understanding of the motivation, then if you review the techniques such as bagging, such as random forest, such as what we will discuss today, maybe the more sophisticated strategy that is boosting. That starts to make sense. Given a data table X, and from this table, we will form the committee A and B. If you let your running algorithm naively, intuitively run on the straightforwardly on the entire data sample, you will end up with one Alice, one Bob, and Bob and Alice always agrees with each other without independent decision making. So maybe a very simple way, most straightforward way is, okay, how about if I give a subset of X, give it to A, and a subset of X, give it to train B. It's not necessarily to guarantee the subsets are 100% independent, okay, separate. We can randomly sample the rows, the data samples from my existing samples. And then we random sample another subset. Maybe they have some overlap, but the point is the two subpopulations are drawn independently from my data sets. And in this way, I give rise to, I have trained A and B. So we have bagging. They are not totally independent, but they are as much independent as possible. Not as much as possible, sorry. They are somehow independent, so that makes the ensemble a meaningful way of improving the performance. Okay, yet another very reasonable way is in each of the training time, do I need to employ all the information I have observed from data in terms of the columns? Not necessarily. Maybe for some of the round, I use a subset of the attributes, and in the next subpopulation, I use only this subset. So that will make the members of the committee more independent from each other. Both random forest and boosting employ such strategies. Okay. So that is the general idea. If you get me here, I'm very happy. If you get along here, I'm very happy. You have almost take every take-home points from today. And the rest of our discussion will be on the details of boosting. You can try to follow. Okay, so because of today's, at the beginning of today's session, we started with some question addressing. So I changed the schedule a little bit. I will discuss the general framework, the main idea of the AdaBoost algorithm here, and we will leave the details later to see if we have enough time. So after introduce the framework of the algorithm, we will go to the quiz and go to assignment 3. And after the discussion about assignment 3, we will take the rest of the time to discuss the details of the algorithm. Okay, so for AdaBoost, the procedure is like that. First, given some data points, maybe I pause that. Okay. What I'm doing, I'm going to introduce independent members to my committee. So what I'm doing, I will resample a copy of my data points. So this is a random resample of the data samples. I just take them to resample them. Of course, there is corresponding y values. I didn't write them out to save some space. Okay, this is a copy of the data, a random copy. So maybe this happens to be X500. This happens to be the maybe 112. Maybe you have repeated samples here. So this guy receives more weights is overrepresented in the copy. That is normal. That can happen. So at the beginning, every sample receives the same probability of being drawn in this copy. Okay, they are the same. And from this copy, we will train a predictor. The first one. This predictor will have a training error. Let's call that epsilon. Okay, then the clever point is Now we give it a weight. So a reasonable thought would be like this. I will give more credit for a more capable predictor. So consider this is epsilon and this is weight. When this is really small, you have a very high weight. When this is really large, which means it is wrong for many times, it will have a less weight. That is reasonable, right? Okay, so we consider binary classification problem. Specifically, we want something like that. When that is 50%. Look, and there is one thing is we cannot get less. We cannot get the error greater than 50% when it is a binary classification situation. Why? Because if so, that means your predictor is wrong, is certainly wrong, so certain that if you do whatever your predictor says not to, such as when your predictor says, okay, the class is positive, then you reach the conclusion, okay, now I will think it is negative. You will have a high accuracy than 0.5. You just flip the decision, okay? Think about that. So we consider the error rate from 0 to 50%. So we want some curve like that. Okay. So consider that as alpha 1. We have an equation for that, but this story is what you really want to understand. The equation doesn't matter that much. We just invent some nice curve, which also corresponding to some very nice theoretical argument. So it is, if you want a detail of that, it is law in this way. Okay, this is basically saying okay, and when we take this to the logarithm, that is based on this guy. So anyway, you have a curve like that. And this is the weight of our predictor. Okay, well, in the next step, the first step is finished. We have a predictor, we have a weight. We then can put that in our pocket. We have done the first step. What's interesting happening is how we prepare for the next step. Okay, we will enlarge or shrink the chance of a data sample to appear in the copy. Maybe next time it will copy here. So this, the second sample, a second copy of the samples is according to another probability. The probabilities are adjusted according to whether, okay, whether the predictor one, the previous predictor, oh, sorry about that, is correct or wrong at a particular X. So let's see if you have W called the weight of Xi. The second one would be some factor. And the factor is according to whether X1 has been correctly classified by the previous prediction. And intuitively, when a sample is correctly classified, then you think, okay, that is not that important. We don't worry about that too much in the next round. If it's wrongly classified, you would think, okay, that is a difficult, challenging example. In the next time, I would put more focus on that, right? So this factor will be greater than 1 if error, smaller than 1 if correct. Okay. So for example, you can make it a simple discussion, you can make a simple adjustment, for example. Okay. Uh-oh, I think I have some synchronization issue. It comes out, it comes out. I have just put two numbers here. I see here, let's do this. I just use it to. Okay. How about if we do this? Good idea. However, the design of AdaBoot is even more sophisticated. You will find this is very smart. Instead of some fixed factor of expanding or shrinking the probability, we let this factor to depend on okay, we let this factor to depend on the, where is, sorry about that. So the screen space is always an issue. Okay. Depending on the weight. And the rationale behind this is that if the previous in the previous round, we try to classify this example, this data sample, and I'm wrong, but the fact that I'm wrong this time, I want to enlarge the chance to appear in the next round of this sample. The fact that I'm wrong in this round is valid also according to what is the performance of the overall performance of my classifier. If this is an excellent classifier, it is correct in 99%, but it's wrong on this sample. That means this sample is really difficult. the fact that a good classifier has made mistakes on this sample means this sample really needs to be overrepresented a lot in the next time to put focus on. On the other hand, if the classifier is a bad one, a poor one, it is close to random guess and it's wrong or right, does not tell too much about how difficult of the sample is. It is only about its own quality. In this case, I would not like to mess up my width too much according to those low quality classifier. Okay, so what I'm going to do will be, instead of using these two fixed value, I will use so now we have made this loop. Okay, so the and you can see there are several interesting design choices in the entire process. So let's take a review. We want to form some independent committee, and the challenge is to form the committee members using limited data sample, okay, and let them to be independent, and make a system, let them to vote. So what we are doing here is, first, we randomly sample from our data training data set, a subsample, train a weak classifier, and give it a weight according to how correct or incorrect it is. And then we re-weight our data samples for the next round of such training and weighting. And the re-weighting is done according to whether a sample has been correctly or incorrectly classified in the last round. Okay. And the correctness and incorrectness is weighted by the performance of the last round predictor. So that is the story of AdaBoost. Okay, are we on the same page right now? I got some very nice discussion in the chat box. I'm very happy. So yeah, you can. I think some of the discussion is somehow really spot on. So perhaps after the class, you can try to implement your idea to maybe test this way or the other. And anyway, you may discover some interesting thing, or at least you may start appreciate the existing design. Okay, fine. Well, we still have 45 minutes. So let's do our quiz first. And after the quiz, we will discuss assignment 3. And after that, if we still have more time, I will demonstrate how to well, implement that idea in computer software. Okay, so our quiz. Yes. I don't want to discuss question one too much because we have just studied that in class. That corresponds to our discussion here. We have 3 members in the committee and they have some chances of making errors or being correct. Well, then it asks the chance of making errors of that committee. We have calculated that. That is 10.4%. And in question 2, so yes, please read that later. But the point is some of the wrong answers is just to try to remind us some misunderstanding. What I'm trying to say is that we do not have independent training data set. That is a luxury we want, but we do not have. And because of some empirical or reality difficulties, we hope the ensemble is better than individual ones, but we do not have that guarantee. And in reality, because of the reuse of some data samples from the resampling from time to time, the weak classifiers, they are not independent. So this is the correct answer. And this one is just disagree with the previous one. So it says the classifiers are the independent. That is wrong. They are not independent. And question 3. Is for the edibles. And it refers to one fact that some data samples, like the like the example here, some samples can reappear in the resampled copy, so that it is overrepresented. Overrepresented means by letting it appear twice or 3 times in the sample, when we learn the next weak classifier, we tell the learning algorithm in such a way, you need really be careful about this guy. If you mess up this guy, you will receive a penalty 3 times or 4 times, whatever. That means overrepresented. So, yeah, that is what I mean. We do not need to remove the repetitions. Okay, it's the repetitions are expected and valid. Summarize. The overall chance of making errors is 10.4%. And in question 2, the training data sets are resampled from the same one. We do not have luxury of multiple training data sets, and the ensemble is not guaranteed to be better than the individual one. Just a hope. and the weak classifiers are not independent. So question 3, repetitions in the resampling is expected. It's a feature, it's not a bug. Okay, where do I submit my? Okay, so. Good. Okay, this is our quiz. And let's consider assignment 3. I have announced it. Oh, no. So what they are going to do is you will make a video discussing the answer of 3 quiz questions. Okay, I will make the quizzes available after a while, after the 10 weeks. Sorry, I will make the quizzes available. Then you will have time to okay. I think the date of the assignment has changed a little bit. I will make all the quizzes available, and in the next week, I will discuss all the quiz questions of both the week 9 and week 10, so that you can do this assignment. Okay, so you will be randomly given 3 quiz questions, and you need to discuss those questions, 2 minutes each. And you need to understand the question and answer it correctly and give some explanation of the answer. So you can read some of the criteria here. It's a if you do not, I cannot give, because the questions are different from each other, and by the nature of the questions, they are different from each other. So I cannot give you a general guideline. But fortunately, every single question has been discussed in class. So if you do not know what to do, try to review in the class and see how I did explain that. Okay, so you have 6 minutes to do the explanation. That is the maximum time allowed. If you can explain, you can explain things clearly in shorter time, do that. Okay, and you need to spend another 30 seconds to show us that you are doing the quizzes you are required to do. So the quizzes is in this way. Show you. You copy this piece of code. Where is that? Okay, if you run that, it will give you some quiz questions. It will give you 5. This printing is not very helpful. I think I prepared that in another notebook, which when you print that, it gives you some rump text, but that is not the big issue. You can write a for loop. I will add that. Okay. So in this case, you are given these 5 choices. You can choose 3 of that, such as A1, quiz 6, question 2, quiz 5, question 3, quiz 8, question 1. This happens to be this one we have just discussed, the committee one. Okay, anyway. So you won't be able to get the question right now because the magic number has not been announced. After the deadline of assignment 2, another announcement will come online and you will be given a magic number. Okay, put the magic number here. See, for example, it is 42. And put your student ID here. This is just an example one. So it will generate a random set of quiz here. You can freely choose 3 out of the 5 and explain the quiz questions in the three quizzes. Okay. You need to include the generation of the quiz in your video. How to do that? You need to do a screen recording. It depends on you. You can find some technical solution for that. I personally often use what is that? It's called OBS. This one. OBS screen recording, but I'm using a Mac computer. I'm not sure, but I'm sure this could be easier on a Windows computer. And OBS is an open software, so probably it is available on Windows as well. But this is really depends on you. You can screen recording this, and well, then you can continue your screen recording and open those quiz questions and start discussing each one of them. So yes, any questions about that? Oh, there is no page limit for assignment 2. You want me show the step to calculate the first question? There is a request for me to calculate this number here. So show you. Basically, you have the situations of for Alice, correct? So Alice, Bob, and Charlie, they can both to be correct or incorrect, right? These are all the cases. Okay, so then you give some probability. So let it to be correct if 0 means correct, or maybe 0 means incorrect. Okay, so If A is correct times, if B is correct times, if C is correct. Okay. Now it is very easy to collect them. So right, then we do so if at least two of them are correct, then right, then so that is how that has been calculated. I have a question. Do we need to explain it with code? Explain the quiz questions? No. It's a. Please review the previous sessions. How I did explain. How I did the explanation. Probably you can do something similar. You expect that to be 42. You will get the magic number after the deadline of assignment 2. That should be midnight, 4th October. The due date for assignment 3. Ah, dear. Did I due date. I probably I haven't I haven't put the due date here. My fault. I haven't set a date here. I will set it after I check the subject outline. That will be exactly the same as stated in the subject outline. Please check subject outline. So maybe put it here. The due date is 17th October. I'll set it here right now. Okay. I have other questions about its screen recording. You do not need to show your faces. It's a screen recording is sufficient. Oh, some suggestions about OBS. Thank you very much. But but I'm not an expert in this video audio settings. You can use whatever you want to use. I'm sure you guys are better than me. I bet you watch some like the Twitch or YouTube live stream of people playing video games. You probably will be better off trying to ask those people how to record your screen while you're playing games. If you can do that, you can definitely do the explanation. Well, only the next question is, can we take a screenshot? Well, I think probably yes, but I'm not sure if that will make the life easier for you too much, because at the end of the day, you need to record the audio and also put the audio with the corresponding screenshot. So probably it's easier to do the screen recording, but that depends on you. The Python code, if you read the code, yeah, the code randomly pick 5 quiz questions. You need to show the screenshot or the screen recording that you run the code, and the code spit out, print out the 5 questions, and you told us I will choose that 3 out of the 5. Okay, I think I have set the magic number. Faces screen recording. I have a inquiry. Say you want an overview of random guessing for a decision tree. So please try to clarify the question in the QA time. I didn't get that right now. And there isn't change of the deadline of assignment 2, no. Yes, of course. The next question is, can we draw things while in the screen recording? Yes, that is encouraged. There is a, can we run the code again to randomly get another 5 questions? So no, yes and no. Yes, it's you probably not be here to and you probably not get another point in this subject that I have sometimes discussed, the random number generation. This is well, not directly inside machine learning, but it's a very relevant skill that we want the random generator always gives us the same but random numbers. Like here, if you run that multiple times, the result won't change. Because here the point is to seed the random generator. Look, you can use the scale to debug your machine learning technique. Why you need this scale? Remember our discussion here? Machine learning is inherently a random business. The randomness comes from here, and sometimes there is some random factors here. So that makes when things go wrong, it's very difficult to debug. And give everything a seed makes the output of the algorithm deterministic, but random. Well, but following some random distribution. Okay, anyway. Yes, you can. Next question, can we load data from GitHub repo? Yes, you can. But in any event, please, the general principle, the bottom line is your grader, we have a team to grade that, needs to be able to just hit the wrong all and everything just up and running.
Jun, just clarifying that. So I had originally I was loading data through my drive, and that would need the marker to update that link if you mount in the drive. So that workaround, I can just upload to a GitHub repo, and then if you just run it all with that link, is that all fine? Yeah, if you click run all and it just goes through, that's all good.
Yes, that's good. That's good.
Okay,
yeah,
perfect.
Yeah. Yes, you can use multiple data sets for assignment too. You can. Okay. So pretty much, okay. Still another one. Last one before I try to use the rest of 20 minutes to show the AWS. Okay. So if we use real data set, do we just mention it in the report? You just need to mention that in the report. You do not need to let me know before you use the real data set, unless your real data set has some privacy issues, but I assume that is not your case. You do not need too much visualization. Okay, we'll probably back to our point here. Yeah, let me clean everything. Restart. So okay, yes. Well, in this example, let us start to consider some more sophisticated data. What I'm doing is like this, just to show that all the discussion in this subject so far has been on toy data set. However, that's not necessarily the case that we always need to visualize the data space. Sometimes we just need some higher level understanding of our data, and that is okay. What we will use is some images here. Specifically, our data samples now, consider this, will be a table, and the table has 64 columns. So the 64 columns corresponds to the, where is that? This corresponds to the pixels here. This corresponds to this pixel. Go, so on and so forth. You have 8 by 8 pixels in each image, and you have 64 attributes. Okay, so basically, our data is um, 273 samples. Each sample contains 64 attributes. And also, I have simplified the classification problem into 2 classifications to demonstrate the above in this case. The classification is in this way. If the digit, this is handwritten digits, and you can read it somehow. When it is 5, we tag it as negative. When it is 1, we tag it as positive. So that is the problem setting. Okay, and here shows what it's like of the 64. Okay, this reshape means, well, previously if you just print out the first example here, see, you will have 64 numbers represent how how much ink has been distributed to a specific area represented by that pixel, which represent to the brightness of the pixel on my screen. And these are just the 64 numbers. Although you can see there's a array-like stuff, but actually it is not. It's just the artifacts. Nice of printing the very long thing. If I allow that to print this long, this will be a very long string of numbers. However, if we reshape it into 8 by 8, it now has structures. It has rows. I'm not meaning the rows of the data table. No, that rows means different numbers. What I mean here is the rows of pixels in one number. So now we have 8 by 8. Okay, and we have 8 rows. So in this format, we can take a look at the specific image structure of the data. And what I'm going to do, I'm doing some very brutal force simple thing. I will try to classify the example by taking contrast. Okay, how about let us just contrast the example. See, I just this is just my hypothesis. Okay, my hypothesis is if I consider the left-hand side of an image and contrast the brightness, the overall brightness of the left-hand side with the right-hand side, I will get some difference. And maybe the difference is different from the samples in 5 and samples in 1. So let's try to somehow verify or test my assumption here. Let's see if I take the x train 0, this guy, and I take the left-hand side. That means every row of that sample and every row of that sample and every row and the left-hand side. So here to the so look, there are 2 pairs of the brackets here. The first pair is representing the input of the reshape function, and second pair is that the function receives an argument of a tuple. A tuple. Okay, so I first reshape that 64 numbers into 8 by 8, and then take all the rows of the 8 by 8 and take the right-hand side of each row. So what I'm doing, I'm getting 4 columns of 8 rows. Okay, then I can take the sum of that. It is this. And I can take the right-hand side. So I have omitted this. Okay, that means from the beginning to the 4th column, that is from the 4th column to the end. So let's take those and have a look. Yeah, they have some difference. Let's do this. Sure. And let's see if our sort is correct. Say, we scatter. Maybe so we will consider a sample I. Oh, we do not have an I here. Consider the first sample, and the first sample is belonging to the negative class. And here we put a dot here in the negative one, representing this. Okay. Actually, we do not need color here, so we can do the for loop of the I. Just to verify if we do things. Look, it seems that, okay, the color does not matter anyway. That, well, this is some, well, distinguishable feature, right? It's not that useful. Look, there is overlaps, like when the difference between the left-hand side and the right-hand side is, for example, 0, that can be both the negative and the positive class. However, overall, the negative one is for the negative one, this difference is a little bit larger, and for the positive one, this is a little bit smaller, right? So let's realize this idea in a more systematical way. What I'm going to do, well, is try to do mask. And that it will be np dot zeros. I let this. Sorry, mask 0. I give it some map. So use different colors, make it clear. Okay, I will take the bright side and use the bright side to subtract the dark side from the bright side and take the sum of that. What I'm going to do is okay. If I'm using this 2 times this. You can see this takes the left-hand side of a sample. You can just take the sum of that. And on the other hand, you can use 1 minus that. Right. So we can then take the subtract the sum of the second part from the sum of the first part, and which will helps us to do the same formulation here. So what is the point here? Is that if I employ different masks, that will be corresponding to the idea of how about if we take the different attributes of samples. Okay, what I'm going to do is using different kind of masks and see how they work on the classification problem. I'm using this different kind of masks. The first one is just what we have done, and this one is like that, and so on and so forth. So my weak classifiers will be the my weak classifiers will be one of the masks, and I will train the weak classifiers on my data. See, for the first step of AdaBoost, sorry about that. I'm taking a copy of the training data samples. Okay, well, these are the resampled copies. So what I'm going to do here is apply. So this contrast classifier is just to use the previous, sorry, where is my contrast classifier? Okay, it's just implement the previous discussion. We use the bright, we subtract the dark part from the bright part and summarize everything. If the difference is positive, we return 1. If the difference negative, we return -1. So that is what it is doing. And there is another piece of logic here that is, remember our discussion here. The epsilon must be smaller than 0.5 for a 2-class classification. That means if according to the previous classification rule, the accuracy is less than 0.5, that means that rule has been valid but applied in the wrong direction. We just flip the decision. That means when the difference is less than 0, then we return negative. If it's greater than 0, we return positive. So that does not change the nature of the logic, but just flip the classification direction. Okay. And according to that, I can show you the first prediction. Oh, sorry. I have used the mask of the mask of that. Use this mask. The left and the right contrast mask. The first big prediction is that, and the correctness will be accuracy 1. What's this? Okay, and that's it. So that is the correctness of the first predictor. Okay, and here we do some, we put things together a little bit. What I'm doing is we will try the prediction and the evaluation of all the templates, and then we select the best one as the weak classifier we use for this round. Okay, so the best template is the up, the bottom up contrast. So this is the flip or not flip. It's just it's not important. And the important thing is here. So we now have a according to the accuracy. Where is the accuracy? I don't think I have printed that out, but according to the accuracy, we have calculated the weight of the classifier using the equation here. Okay, so that is 1 minus accuracy, which is the correctness, divided by accuracy. Here is a small constant for numerical safety, and this is the equation here. And in the next, we will apply that classifier on all the training data. This, recall that this is all the training data. This is not the resampled one. Where is that? Okay. Sorry, where is it? Fit. Okay, I'm not sure because I think that happens from the previous example. Sorry about that. You should fit the classifier on the resampled copy, but I think from some example I have maybe in the last class I have modified a little bit. Let's rerun that. Sorry about that. This time it selects this one. Okay, and importantly is that we will use the selective classifier on all the training data sample. Okay, and the error will be, this actually should not be named as error. This will be the direction to which to adjust sample weight in the next round. So this is a little bit lazy, but that is what it means. That is, if it is correct, then it's going to shrink the probability of next, not of the chance of being selecting the next time, and otherwise it will increase the chance. So keep this, think about that. Use this name. So like for the first one, it has been classified wrongly. You see. So look, this sample has been classified wrongly. So in the next time, in the next run, it will be given a higher weight. And this is classified correctly. In the next round, it will be given less weight. So here is the factor that will be applied to the weights. We need to normalize it so that the probability add to 1. Okay, so putting everything together here is the full implementation of the idea here. And you can see that it starts from some really mediocre, so not very good weak classic predictors, and it can improve its performance. I think later it will reach something, yeah, in the way it reaches something that is close to 80% anyway. So this is just a sample example. And in the next, I will have used the decision tree, but only depth one decision tree. That means I can test only one pixel of each sample using this to do the classification. And you can see this will build strong classifier really quickly. Okay. So yeah, I'm 5 minutes over time. I hope that gives you some understanding of the algorithm. Okay. So I'm still here for a little while longer to address questions. Anyone of that? I have some people ask me about the missed consultation hour yesterday. I'm not sure if I have already addressed your questions today. Nicholas, yes.
Should I just send you an email?
Yes, Nicholas, yes.
Yeah, because I've got to go now, but I'll have some questions a bit later.
Okay.
Okay, I'll send you an email. Thanks.
I also sent you an email. Can you check it a bit later?
Yes. Have you booked yesterday? If you didn't book yesterday, I can. However, it's not guaranteed. So,
Yeah, I know. You know, like I know, but you know, just I understand about it.
yeah. I'll try, but yeah, this is mostly for to make up for the last consultation. There is a question, and yeah, for assignment 2, you can use the code, but you can use the code from GitHub. We have a version of this class on GitHub, but that was from 2 years ago. If you mean the code of that code, yes, but any code is also yes. The point is you need to understand the code and interpret your understanding in the report. And also let you know, Anton and Gitas run consultation hours every Wednesday and right after this session as well. If you have questions, please, especially if you have questions about your coding things, you can attend their sessions. No, it won't be a one-to-one session later. It's mostly for people who booked the yesterday's session, but somehow get missed. But if you can send me an email to see if I have some time later today. I have a question about if you need to use 2 data sets to get an HD. I think 2 data sets is definitely helpful towards an HD, but the points allocated of using 2 data sets is not that much. If you read the criteria, probably 2 points for using an extra data set. But definitely, if you can, why not? Because the effort of after you have implemented everything for the of the algorithm, apply that to another data set won't be such a big deal. Please do that.
I have a question.
Yeah.
Regarding assignment 2. So the first question is about the referencing. So for the referencing, for my case, I use some concept from Canvas. I mean, like, you know, the Canvas.
Mm-hmm.
So do I need to put the reference for that, or do I need to put the reference on that, or do I need to do something else?
Have you directly copied the?
Nah, I mean, like it doesn't appear in, you know, similarity, but like, for example, I put, you know, what is the definition of, you know, like entropy, what is the definition of information gain, but obviously I wrote in my own word, but
Mhm.
anyway, I learned from Canvas, so I'm not really sure whether I have to, you know, put the referencing on that or not.
If you are not 100% sure, put a reference, because if you put a reference, it does not take too much. You just like add a
Yeah.
line. Here is from this source. Yes, or on the safe side.
Do you want us to use like very specific type, like for example Harvard referencing style, or
No. You can use any. Well.
so it means I can just use IEEE style, right?
Yeah. IEEE style is good.
Yeah, I prefer that one.
Yeah. Nowadays, you can have maybe tons of open source papers on Archive Archive. So you just follow any the standard style there. You do not.
Oh, you
need
mean
to do anything.
RSI, right?
Yeah. This.
Okay, so another question is, for the code itself, I use some concept from Stack Overflow. I didn't copy, but like I didn't know how to convert NumPy into, I didn't know how to convert NumPy into pandas data frame. So for that one, I use some concept from Stack Overflow post. Do I need to put the reference for that?
Stack Overflow post.
Yeah, Stack Overflow, right?
Yeah.
So I googled how to convert, like
No. For that, everybody copies Stack Overflow answers.
I mean, like, I didn't copy, just I just copied the concept, the idea.
Yeah. You can copy Stack Overflow code, and this is it's a common practice. Don't worry about that.
Okay, got it. Yeah. Well, thank you so much. That's all.
I have a question.
Yeah.
I mentioned earlier in the lecture that for one of my data sets, I received an accuracy of 98, 99. And
Yeah.
for the second data set, I had 48% accuracy.
How many classes?
It was the wine data set. And I did trained it on the iris data set, and then also use the wine data set as well from sklearn library.
Mm-hmm.
And it had a 48% accuracy, and I'm just wondering if that's okay, or if there's something else I need
For
to
the
do.
one that said 48, I from my memory. Is the one data set has a class imbalance? Maybe. Probably you have some bug in your implementation. That is what I can see, and probably the bug is minor. It's not a major one. So if I'd say you could lose some points of imperfect, but that would be minimal, something like 2-3 points at most.
Okay.
Because yeah, we judge according to your understanding of the algorithm. We do not mark according to accuracy. But when you have minor errors, you get some deducted points.
Okay.
It won't be too much.
So with that as well, when I made that comment, you mentioned discussing the randomness of the data set, or the randomness of the algorithm. And I was just wondering if you could clarify what you meant by that.
The randomness of the data set? Oh, which part? Sorry.
You mentioned random guessing, that the algorithm does random guessing.
In the discussion of the learning framework. Oh.
Okay. I think Harrison's answered it a little bit.
Okay, if you want, I sometimes I emphasize several times that for a particular test sample, X test, the output, for example, if I have picked up this particular test example here, and I do all the things like learning, test, evaluation, whatsoever, I delivered an algorithm. And this, the result of applying my algorithm, I give this to this, and then this will give out some prediction here.
Yeah.
So if you concentrate only on the output of this is the input, this is the output. If you concentrate on this output and try to summarize whatever in the learning whatsoever here, so only summarize that away, only take this. So this output is a random number. This is the input, and this output is a random number. This is random because the whole learning process is inherently random. That is not mean, this is not mean, I'm not trying to mean that my algorithm just output a random number for the input. No, that is not what I'm trying to mean. What I'm trying to mean is if you think that I have a lot of hypotheses, even each of the hypotheses will generate deterministic output for the input, but I do not have certain control which hypothesis will be selected as the delivery of my learning process. Yeah. Because why? Because the selection criteria is according to some quality control. It is like if I'm a factory, I will produce machines, and my machines will work on this input and generate outputs. However, as a factory, I'm running a business. I cannot solely control what my customer will have. I'm a factory, I'm not a dictator. I do not just give you a machine and you use my machine. Yeah. You are my customer. You give me some quality control. The quality control, you can think that as your training data. You instruct me, not me instruct you. You instruct me, look, your machine must work on my training data. Because of this requirement, I lose control of what machine I can produce to you.
Yeah.
So that is the fundamental randomness.
Okay. And my question also extends to, in the report, should we include a section about recommendations for future improvements that could be made to the algorithm?
It definitely helps. Yeah, it's not, if you do not have that session, you do not feel the assignment, but that session will definitely help.
Yeah, okay. So if I write of the things I could do to optimize the algorithm to make it better, it's worth including that in the report.
Yeah.
Okay, thank you.
Hi, Jen. I had a question about, like you said, there's a mark allocated for using a separate data set. Do you mean a separate data set by like referring to like training and testing data set? Is that what you mean?
These are two.
Or do you mean like one, like two separate data sets, like two separate data sets, like two separate real data sets, a toy data set?
I understand what you mean. Okay, this is an extra data set. This is a split data set into training and test and validation.
Yep.
These are two orthogonal directions that you can improve your report.
Yeah.
They are they are not contradicting with each other. If you have maybe two data sets and you split the two data sets each into 3 parts, training, validation, test. Then your algorithm will run on 6 parts.
Yeah. My question was like, so the mark that is allocated will, I think it mentions a separate data set has been used to verify the learning result. So it's not.
Sorry, my fault. I think the verify the learning result does not mean to verify the learned model on one data set. It's not the same. It's to verify the
Generalization of the.
no. This is verify your implementation of the algorithm that can work on 2 different data sets.
Oh, okay. So that particular, so in the marking criteria, 0.4 is for checking on a extra data set, like a completely different. Okay.
Completely different, not the same.
Okay, yeah. Thank you.
A quick question. So are we allowed to modify the tree building algorithm to apply certain sort of enhancements? The enhancements sort of being like trimming nodes after construction, or making sure that the distribution of nodes is balanced rather than left or right biased. So long as we follow the core steps outlined in the algorithm, right?
So those are all good improvements. So what is your question?
Are we allowed to apply those improvements?
Yes. But for one thing is I didn't catch very clearly about your meaning about the balance of the sample between the tree nodes, because our tree is not the same as the tree as data structure you have learned in the data structure and algorithm, whatever the early subject. Our tree is not to store data. Our tree is to process data. So it cares less about the balance or imbalance. But of course, you could have some good argument about the balance of the tree, such as maybe instead of focus on the greedy procedure of always optimize for the information gain of individual step. However, perhaps I want to invent something that can help to minimize the overall number of steps, not only for individual sample, but for the distribution of the data. That can make sense. However, if you want to store information, if you considering storing information in a balanced tree, that is different. It's just a reminder.
Okay.
Yeah.
Okay, cool. Thank you.
Okay, I got quite a number of questions about the second data set. It was a kind of it was something that I'd like to help you to get more points, because think about that, you have already implemented an algorithm and a training and test procedure of the algorithm. So it is relatively easy if you keep everything intact on one data set, and then you just apply everything on the second data set and report the result. It isn't includes much effort, but if you do that, you get some extra points. However, the point isn't that much, only 2 or 3 points. You are not required to do that. If you do not do that, you probably also get a very good result if everything works fine for one data set. I get another question about bagging uses randomly on sample. You mean randomly resampled data set? So the classifiers are independent, right? No, not right. The randomly resampled data set, well, it kind of try to get independent classifiers, but the question is from where you resample the data set. Okay, because at the end of the day, you have only one training data set. All the resampling happens from this source data set. If you resample from the same population once and once again, although the resampling is random, but the result is inherently connected to each other. You cannot get completely independency from that. Another question is, what if I had a lower accuracy in the second dataset? That is totally expected. The difficulty of the task varies from one dataset to another. Is okay. Another question, also the second data set. Yes, if you use one, your algorithm on Iris, and for the second one, you use the same model. Yes, yes, by just providing the training and the evaluation procedure, another source of data is that the effort is not that much. And of course, you by doing so, you would learn something. You will find that although in principle they are very similar, and when we discuss in class, the principles of the algorithm always remains the same. But whenever you try to apply things in practice, things get hairy very quickly. You will find maybe everything works okay on the first data set, but when I try to apply that on second one, why things just explode? What is that attribute that contains missing values? And what is that one? That one is a categorical attribute, but my algorithm is only for continuous values. You will quickly find, this data set won't work. But I really want that 3 points. Then what do I do? So, you know, there is a kidding talking in this field. You want good result? No, don't worry about model selection. That is very difficult. Do data selection. So that is probably some of you will do in the assignment. But the point is, please try to appreciate that challenges. And in real life, you don't have the luxury of doing data selection. You have to do somehow working on the model. I have another question. Are we allowed to handle both categorical and continuous in the same algorithm? Yeah, you are encouraged to if you can. It's a challenge. It's not a privilege. It's a challenge. It's a duty when you are in real world employed as a data scientist or somehow. Similar rule. Okay, I think we still have a number of people with me. So if you still have coding or anything else questions, please move to Anchen's session. He will be able to offer help as well. Okay, so yes. For the data set, you start with the scikit-learn data set. It is very helpful for new learners. And also, of course, you can always be checking on the Kaggle. Okay. See you next time. Bye-bye.